This is review video 39, Dissolution and Enthalpy. So to remind everybody what a dissolution is, it's when a solute dissolves into a solvent. So solute, this term right here, just to remind you, means the thing that is being dissolved or the thing that is in a lesser concentration, versus a solvent is the thing that is causing that dissolution or doing the dissolving, or the thing that is in greater concentration. So again, we can have solid solutions, we can have liquid solutions, aqueous solutions, gaseous solutions, whatever, but most of the time when we talk about solutions in this class, we are talking about aqueous solutions, or solutions where the solute is dissolving in water. So most of the time, our solute is going to be a solid and our solvent is going to be a liquid. Again, most of the time it's going to be water. And we can see an example of that here, where we're seeing our ionic solid, sodium chloride, dissolving into water. So we can see those sodium ions and those chlorine ions breaking off and being surrounded by those water molecules. So to do a dissolution, it requires energy input, right? So we need some energy input, the endothermic portion of the dissolution, to break the molecular attraction between whatever the solute is, whatever the solid substance is. So if we're talking about an ionic substance like that NaCl from earlier, we're talking about ionic bonds having to break, or the association between these oppositely charged ions. All of that would be breaking for those ions to dissolve. If we're talking about a molecular covalent substance, though, like this sugar over here, then we're talking about IMFs that are breaking. So we're breaking a molecular attraction of some sort. It's just a question of what kind. And we can see our IMFs represented by that dotted line. So if those sugar molecules were to dissolve, that would be what breaks, not your covalent bonds between each atom within the sugar molecule. So that's the endothermic part. However, dissolutions also have energy output as well. They have an exothermic portion, and that happens when intermolecular forces form between whatever the dissolved solute is and the water molecules. So again, if you're talking about sodium chloride, the NaCl that's dissolving, you're going to see some ion dipole forces that are going to start forming between your dissolved ions and the water molecules. So you can see the attraction here between the sodium ions and the more electronegative oxygens, and we can see the attraction between your chlorine ions and the more electropositive hydrogens of those water molecules, right? And again, if we're not talking about an ionic substance, if we're talking about a covalent substance interacting with water, that IMF will not be an ion dipole force, because sugar dissolving in water, well, sugar's not an ion. So then that might be a dipole-dipole force or a hydrogen bond, but some form of IMF between the dissolved substance and water will take place. When we consider dissolutions as a whole, their endothermic and their exothermic portions together, we have to consider which one is greater. Did it take more force to break the bonds, or did we release more energy when we formed those IMFs? And when you have an overall endothermic dissolution, that means that the energy input that it took to break the bonds, or like break the ionic bonds of the ionic substance, that is more than the energy output, or the IMFs, upon the formation of those ion dipoles with water. So again, endothermic means your input is greater than your output. Overall, if you have an endothermic dissolution, your delta H value will be positive, because overall energy is being absorbed to complete the dissolution. And as a result, your surroundings are going to get colder, because that system is overall absorbing heat energy from the surroundings. So you would record a temperature decrease on a thermometer with an endothermic dissolution. Conversely, when your dissolution is exothermic, you have the exact opposite. Your energy output is greater than your energy input was, meaning your delta H value is negative, and your surroundings are going to get warmer as your system releases energy overall. So on a thermometer, you would see the temperature increase, because your thermometer, the surroundings, got that energy. The surroundings absorbed the energy from the system that released it. Really quickly, just point of fact, you need to remember this. When you are doing a Q equals MC delta T calculation for a dissolution, just like we did in the lab, you want to remember that your mass, your M, is the mass of the solute and the solvent together, because you need both your salt and your water to do the dissolution. So you have to consider the mass of both of those things. 9 times out of 10, the first mistake I see when people are doing this type of calculation is they'll only use the mass of the solid, or they'll only use the mass of the water, when in reality you need both. If you have any questions about these topics, please feel free to ask.